All right, so let me set the video. So we're talking about impacts, right? I just brought this quickly go over. We're talking about impacts. I went over these in last class just to refresh your minds. So there are two possible outcomes. One would be if these two objects that are involved in this impact, they adhere together, they stick together after the impact. That was the outcome one, and there's only one velocity we have to calculate, and that's the velocity after the impact. Then we had a case, or we can have a case where these two objects, they do not stick together, right? That case, in that outcome, there to say, since I use the word case here, there are two possible cases. One is the direct central impact that I talked about, and the second one is oblique central impact, right? And central impact is there. That's all we cover in this course. And we talked about each one, how to deal with each one. The reason I want to go over a couple examples today is that there are a few things about these velocity vectors that you really have to be cautious, and you have to pay attention to directions and positive, negative signs. That's somewhere that things can go wrong, right? The general story is not very complicated, but these signs can throw you off. I can throw anyone off, right? So you have to really pay attention to axes, your plane of contact, your line of impact, see which direction is positive, which direction is negative, and take those into account. So if you look at the direct central impact, right, pay attention that the equations I put there are for the case where VA, VB, and VA prime and VB prime are both towards the positive direction before and after the impact. Right. So if you have a situation that your V vector is not in the positive direction, you have to take into account that negative sign. Right. The same story about oblique central impact. Right. We said, well, in X direction is similar to direct central impact because the impact happens along the line of impact, or in X axis, along X axis. So you have to pay attention to signs. So when you write these equations, just pay attention that how to implement those signs. Let's put it this way. All right, I'll go over examples and we'll see. And in Y direction, we said there is the velocity, or the moment is conserved. So the velocity before and after the impact is they are the same along the plane of contact. All right. And this is a special case. Well, that's the example we're going to go over. So let's go to the example we're talking about. We said there is this ball falling down, right? So perfect vertical motion, 10 meters per second downward. It hits this inclined surface. The surface creates an angle of theta with the horizon, and then we are tasked to find the rebound speed, or V2, the velocity after the impact, and the angle it creates with this inclined surface. Okay. All right, so this is the special case. Actually, this is a special case. Sorry, jumping back and forth between pages. The special case, we said, well, if one object, if one of these objects that we have in this oblique central impact, right? This is an oblique impact because the impact is not happening, or both objects are not moving along a straight line. Right? They're like they have some angle when they hit each other. Now we said, well, the special case would be if one of these are just some stationary object. Right, so all you got to do is just to plug in the velocity for that stationary object, 0 before and after the impact. Right, that doesn't move. So just one object, or one particle, one rigid body is moving only. So that's basically the same thing. Only one thing is stationary. So just put the velocity before and after the impact 0. Now this is that special case, right? We started with that. As I said, the first thing you do, you identify the plane of contact and line of impact. Right? Plane of contact is where the contact happens. Line of impact is perpendicular to plane of contact. Right? Now, part A is asking us to find the velocity after the impact and the angle that velocity creates with this surface, meaning that, well, basically it's asking us to find the velocity after the impact, right? Velocity vector. We want to find its magnitude and its direction. So I'll start with what I know, right? What the equations I have. So for this case, well, that's an impact, oblique impact in y direction. The moment is conserved. In x direction, we are in this special case. Right? One side is stationary, the other side is moving. So let's start with y direction. Right? We have velocities. We said velocity in y direction is the same before and after the impact. Right? So if I go here, well, b, let's call this b. So we can use our own notation there. Let's call this object b and let's call this object a. Right? So I'll say va prime in y direction. Right, the velocity, well, let's just start with velocity before, is equal to velocity after in y direction. Or you can just write it ma va is equal to ma prime ma va prime. Right? I just canceled, we can think about it this way, canceled m from both sides. So from there, that's where I wanted you to pay attention. All right. So this angle is theta. As a result, this one is theta. Right? So that one we know. So we can actually find the velocity before impact for VA, the components of velocity along plane of contact and line of impact. Right? If I do that, you will get, if I use the color this more. So this would be, put it this way. This would be your V, I'll call it, I refer to it as VA. Again, just to stick to our own notation. VA, Y, and this would be, pay attention to the direction of these vectors or components, better to say, VA, X. All right. Now, VAY is negative, right? It's in the negative direction. If Y is positive this way, so that would be negative. So someone tell me how should I continue this? What is VAY? Too early in the morning, right? Let me ask a question so wake some of you up. And myself. So VAY, what is VAY? Knowing that we know VA and we know theta.
Wouldn't it be VA sine theta? Oh, sorry, V1 sine theta.
Yeah, V1 and VA is the same. I just assume that it's V1, but you can just write V1. Yeah. So that would be V1 sine theta negative, right? We are in negative direction. So that would be minus V1 sine theta, right? If anyone disagrees, just tell me now. So now we have to, right, this is A. Just want to make sure this is particle A before impact, after the impact. Hits the surface, rebounds. Now VAY prime, right, would be whatever, let me just put it here as well with the danger of making things crowded. Let's just do it. So this would be this. This would be this. This is going to be your VA prime Y. And this is going to be your VA prime X. Right. So what is VA prime Y? With the information we have there. Yeah, I made it too crowded like this. VA prime is V2, right? It's just, again, it's a matter of notation. It's a velocity after the impact for object A. what is VA prime Y? V2 cosine alpha, exactly, but negative. Again, pay attention to direction, right? It's a negative direction of Y. So minus V2 cosine alpha. So from there, you get one equation. You get V2 cosine alpha is equal to V1, which is 10, times sine 30 degrees. Theta is given, MA is given, and where is VA is in the figure, is on the figure. See, sine 30 degrees. That well, sine 30 is half, so it's 5 meters per second. So this is one equation we got. We don't know what V2 is. We don't know what alpha is. These are the things that we're trying to find, right? So that's that. We got one equation. Oblique impact with some given coefficient of restitution. So this case, right? And the one object is fixed. You know, this is the general case, the equation we have. This is a special case, the relationship between velocities and coefficient of restitution. So knowing that, I can also get another equation. So that it says VA prime X. From there, you get VA prime X is equal to minus E V, I forgot, VAX. And again, the reason I'm solving these problems here, pay attention, VA in this example here we did, VA is in positive X. Right? So the velocity before impact, it has a positive X component and positive Y component. So if keeping that in mind, when you look at this problem, you have to pay attention to sign. If it's not in the positive direction, then you have to take that into account. All right. So from there, we VA X prime is V2 sine alpha, right? And it's in positive X, so we're good, is equal to minus E. Now VAX, velocity of A before impact along X-axis. That's that orange arrow along X-axis. And see, it's in the negative direction. If this is positive X, VAX is in the negative direction. So that would be minus V1 cosine theta. Right? From there, you'll get V2 sine alpha is equal to, well, E is 0.8. V1 is 10. And this is 30 degrees. And if you plug in these values, I actually don't know. I have to look at my notes, see what I got there. I got 6.928 meters per second. So this is equation 1. This is equation 2. I have two equations, two unknowns, right? You can actually solve this and find both alpha and V2. If you divide 2 by 1, you get tangent alpha, you get a number. From there, you can calculate alpha by calculating the inverse of. So VAX, the reason it's negative, because if you look at the example, so what I want you to do is that when you solve a problem, have these in front of you as reference. Here, this equation, right here, this equation is derived based on VA being in the positive direction, right? If you decompose this VA you get VAX in positive X direction, we get VAY in positive Y direction. So this equation, all the signs and everything is based on VA being in positive direction, both components. Now, if you come to this example, your VA, or velocity before the impact along X-axis, the orange arrow here, this one, this is in negative X direction. So you have to take that into account. That's what I meant by it's very tricky when it comes to impact and the directions. Again, we are talking about momentum methods, so direction matters. Right? So your reference are these. For instance, if you're looking at impact along X-axis or direct central impact, remember, this is for the case when VA, VB, and VA prime and V prime are both positive before and after the impact. So if that's not the case, you have to take into account that sign when you write these two equations. Same story for oblique impact, right? When you are taking into account here, for this example, pay attention that VA is in positive X and positive Y. So if you have a case that VA or velocity before the impact is not in positive direction, or both components of that are not in positive direction, you have to take into account that sign. All right, so from these two, you can find what you wanted, right? Again, dividing 2 by 1 gives you alpha. If we find alpha from either of these, you can find V2, velocity after the impact, or as we call it in the general notation, VA prime. All right, so V2 becomes, this is V2, this is alpha. V2 becomes, hopefully I did the calculation right, 8.544 meter per second, and alpha becomes 54.18 degrees. Hopefully I did all the calculations right. So this is V2 and this is alpha, right? Remember, all the equations you have are just these. Like for oblique central impact, this is what you have. These are what you have. You know, in X direction, there is similar to central impact. You just have to take into account the X component of velocities. And for direct central impact, this is all you have. If they adhere together, stick together, that's pretty straightforward. It's just one relationship. All right. That was part A of this example. Now, part B is asking us to find the percentage of kinetic energy lost during the impact. Right? So what is kinetic energy? Kinetic energy is 1/2mv squared. So basically, what is this part trying to ask or is looking for is asking you that now you know velocity before the impact and you know velocity after the impact. Knowing those two, tell me how much kinetic energy is lost. So that's what this is trying to say. Let me see if I can fit it here. So B, we are looking for the change in kinetic energy divided by whatever kinetic energy we had. So let's say T2 minus T1. T2 being 1/2m V2 squared. This is, can do better, minus 1/2m V1 squared. That'll be 1/2m. M will be no m. M is 0.2. V2 squared. V2 is 8.544 squared minus V1, which is 10 squared. Right. That'll give you minus, let me check, what did I get here? Minus 2.7, like not meter or joule. Right. Energy. Now, you know, change in kinetic energy, you're looking for percentage loss. So you know the change, you know the initial. My initial is just basically 1/2 mv squared. So whatever that is, let me see. So percent loss is equal to delta t over t. This is 2.7 divided by, I don't know how much is that. It's 1 over 2 times 0.2 times 10 squared. Let's go at T1. 100.1 times 100 is 10. So this becomes 2.5, 2.7 divided by 10. It becomes 0.27. This is probably not percent loss. This is loss, and percent loss, just multiply that by 100. So 27%. So because of this impact, 27% of kinetic energy is lost. Right? You know velocity before impact, velocity after impact. Find how much kinetic energy you lost. The percent would be just dividing that by whatever you have. Right? Just trying to explain that. Well, when an impact happens, part of the kinetic energy is transformed into something else. As I said, remember before, could be deformation if you are in an accident, could be sound, could be heat. The energy is conserved, total energy, but it just is converted to a different form. All right. So that's that. Let's do another one. We did an exceptional case that one is a stationary. Let's just do some general example. And both of them are moving, they hit in some oblique fashion, and then find out what are the velocities after the impact. Before I move on, question about this one. So again, pay attention to directions. What we drove there are basically for velocities before impact being in a positive direction. So we have to take that into account when we are writing these equations. Just have to do examples to get a sense of paying attention to the directions. Remember, the first step is to establish the positive directions, establish the plane of contact and line of impact. Once you find the plane of contact, perpendicular to that would be line of impact. Right? And then you know your positive directions, X, you know your positive directions, X and Y. I'll give you a few minutes if you have any, well, I lied, not a few minutes, a few seconds if you have any question. All right. I don't know if it was a few seconds. It was a few seconds. Let's do another example. And an example of two, let's say, simple objects hitting or during impact. They impact. They are in an impact, and then you want to find the velocities. Remember, we said the whole story when I started talking about impact. Remember, I said, well, the whole story is that we know the object's conditions before the impact. We want to know the object's conditions, specifically speaking, their velocities after the impact. That's the main goal when we are studying the impacts of objects. Right? Things can vary here and there, but that's generally the idea. All right. Let's do another example. So we have, let me try to draw this first. So buckle up, because that's going to take me some time to draw these circles. Is that bad? You didn't identify as a circle. Yeah. Let's see how does this go. All right, not bad. Should have been a little bigger, but I think we can live with that. Then we have velocity for this one, this, and velocity for this one like this. This is V let's call this B, let's call this A, this is VB, is 1 meter per second. This is VA, 3 meter per second. Problem statement, it says 2 moves disks A and B having a mass of 1 kilogram and 2 kilograms, respectively, I guess, just to make sure that 1 is A and 2 is B. All right. Respectively, I think the problem sentence continues. Collide with the velocities shown in the figure. Right? How do I draw that? It's 1 meter per second for B in that angle and 3 meter per second for A. Let me complete this picture by putting the plane of contact here. This would be a plane of contact, and this would be line of impact, perpendicular to that. So we call this X, call this Y, line of impact. Let me just not put it there. So we're going to make it very crowded later on, so let's keep it simple. Y is plane of contact, X is line of impact. So we know velocities before the impact, and we're also given the information about if the coefficient of, my handwriting is awesome today, coefficient of restitution for the disks, or probably would be better if I said for this impact, is equal to 0.75. Find the X and Y components of the final velocity of each disk just after the collision. I would say, well, just after their collision. All right. All right. So, can I move this? Probably not. All right. So we have two. Let's say textbook example, but typical example, standard example. Right? You have two objects hitting each other, and then they separate. They basically go their own way after their own ways after the impact. So, oblique central impact. We have to pay attention to components of velocities in both X and Y direction. Well, Y is the plane of contact. Along that, the moment is conserved. So velocities, the components of velocities in that direction are the same before and after the impact for both objects. In X direction, which is the line of impact, we have to write the equation for the impact pretty much, because that's the direction that the impact happens. Right? Let me go back here. So in X direction, all right, we have these two equations. Right? In Y direction, the moment is conserved for both particles, for both objects. So let's just start with, to make our life easier, let's do the same thing we did for previous example. Let's just find the components of velocity for these two objects along a plane of contact and a line of impact, right? Along X and Y. Because these are the components we're going to need: Vx before, Vy, Vax, Vay, Vbx, and Vby. So we know that we need those. Let's just find them. So this is for Va. That would be Vax, and this is Vay. And then let's do Vb. This is going to be Vbx, and this is going to be Vby, right? Oh, I forgot that you need this information, otherwise you can't actually solve this. This angle is phi 45 degrees. This angle is, I think, 30 degrees. Theta 30 degrees. Otherwise, how could you solve this? All right. All right. So in X direction, in X direction, right? I have to put MA VAX plus MB VBX is equal to MA VA prime X plus MB VB prime X. Just to make sure that we use the right notation as well as introduce VA prime X here. And so that's in X direction. Let's plug in the values. We have a lot of information. MA is given, is 1 kilogram. MB is also given, is 2 kilogram. VAX, well, let's find them here. What is VAX? We have VA and we need VBX. Let's find these two. So what is VAX? Three cosine 30 degrees, exactly. Thank you, Samuel. 3 cosine 30 degrees. And it's in positive direction, so we are good. VBX, what is that one? Again, remember these equations are all derived for A, B, velocities in positive direction before the impact, right? So that's important. That's exactly, thank you. That's minus 1 cosine 45 degrees, cosine phi there. So let me see if I have the numbers for this. 3 cosine 30 degrees, I do actually have those. Surprising. 2.598 meter per second. And well, that would be minus the square root of 2 over 2, so it's minus 0.707. This is meter per second. So we know VAX. I don't write it here, but it's right there. We know VBX. Again, we know MA is 1, MB is 2. So we can just rewrite this equation, plug in all the values. You'll get well, VA prime X plus 2 VB prime X is equal to, well, whatever was VAX, which is 2 point something, minus 0.7. I can't do that in my head. I have to look at the number. You'll get 1.184 meter per second. Right? So this is one equation you get. Again, the story, we know conditions before the impact, we want to know conditions after the impact. So the relationship between VA and VB, X components of velocities after the impact, is that VA after the impact in X direction plus VB after the impact in X direction, 2 of VB after the impact in X direction is equal to 1.184. That's one equation, 2 unknowns. So we need another one. Right? And the second one in X direction, remember this X direction, we had 2 equations. In X direction, we can write what we were writing for the impact, similar to central impact. Now it's escaping my mind. Similar to direct central impact, right? And then we have the coefficient of restitution. So we have 2 equations for 2 unknowns, the velocities after the impact. So I'll do that. So I'll go with this equation because I need one more equation. I have 2 unknowns. So that will be E is equal to, E is equal to VB prime X minus VA prime X. I have to double check correctly. Then VA X minus VA X minus VB X. Just double check the equation. VB prime X minus VA prime X versus after the impact, VAX minus VBX. All right. So let's just plug in then. E is, we are given E somewhere, 0.75. So just 0.75 is equal to, well, we don't know anything about the velocities after the impact. We want to find them. So we just plug them in the way they are. We have no idea. Whatever we find will tell us that, both about their magnitude and their direction, right? So whether they're positive or negative. So these 2 we don't really know that much about. VAX we found there is 2.598. VBX minus 0.707. All right. So from there, if you do that math, you should get VB prime in X minus VA prime in X is equal to, well, the denominator multiplied by 0.75. I got 2.8, no, 2.482 meter per second. This would be your second equation, right? So 2 equations, 2 unknowns, right? You're looking for VA prime X or VA, the component of velocity of particle A after the impact in X direction, and component of velocity for particle B after the impact along X direction. So from 1 and 2, you can actually find VA and VA prime and VB prime in X direction. So from 1 and 2, 2 equations, 2 unknowns, you'll get VA prime X as minus 1.26 meter per second, and you will get VB prime X as 1.22 meter per second. All right, pay attention to negative sign, we got that. So this tells me that the x component of velocity for particle A is going to be in negative direction. So after the impact, well, I don't know about y component yet. After the impact, this particle A is going to go to the left. At least the x component is going to be towards left. And for particle B, the x component is going to be towards right. Well, which kind of makes sense logically. When they hit, probably they just hit like this, and then they get separated in this way. Let me see if I can find. Right, so logically it makes sense. So we got the x components. Now we have to get y components for both particles after the impact. Right? And that's actually the straightforward part, because we know that in y direction, and if we had any in z direction, or better to say in the direction of the plane of contact, the moment of particles is conserved. So the velocities before and after, they are the same. So we can write it this way. In I'll go to the next page. I'll come back if you could write if you find in y direction. Right. Whatever is the component for A, right, so we say VA in y direction is equal to VA prime in y direction. Let's find them here. VA in y direction and VB in y direction. That's more like U than VB in y direction. VA in y direction is 3 sine 30 degrees, and it's positive, positive y direction. VB in y direction is 1 sine 45 degrees, and it's negative because it's downward. Minus 1 sine 45 degrees. All right, I'll give you a minute to look at this and see if we look at the figure top and what I wrote here. So velocity in y direction for both particle A and particle B before the impact. And since I know the velocities are, the moment is conserved in y direction, whatever is the velocity before the impact is going to be the velocity after the impact. 3 sine 30, well, sine 30 is half, so it's 1.5 meter per second. This way of choosing colors probably is confusing. I shouldn't have used orange. Because I use orange for x and y components, now I'm just representing y. Should have used a different color. Should I do it? Let me just do it. I think visually it's confusing. So VA y and VA VB in y direction. VA in y direction is 3 sine 30 degrees, which becomes 1.5 meter per second. VB in y direction is minus 1 sine 45 degrees, and that'll be minus 0.707 meter per second. All right. So since we know these, we know also the velocities, component of velocity after the impact. That means VA prime y is VAY, which is 1.5. It's positive. And then VB in y direction is VB prime, or the velocity of B in y direction. That means VB prime in y direction is equal to minus 0.707 meter per second. And these are the y components of velocity. Right. So that's we found what we were asked to. I didn't box this because it becomes crowded. The problem gave us the velocities before the impact, the magnitude and their directions or the angles they were making with plane of contact and line of impact. What we did, we found, or what we were asked to do was that we were asked to find the velocities after the impact, the components of velocities after the impact along X and Y axis, and we found it. So if you want to visually think about it, this is what is happening after the impact. If I can put in this and draw some axes here. If they were, I'm going to be messy and just do it like this. If they're A and B, after the impact, the velocities are, so VA, the component of VA is X is negative and Y is positive. So it's somewhere in this direction. We can actually find the angle. This is your VA prime. And the other one, knowing that this is positive and this is positive. And B, where am I going? B is both positive. So X is positive, Y is negative. That'll be in this direction. In whatever direction that'll be. So it's going to be V prime, where VA prime is, if you want to represent as vectors, is minus 1.26 I plus 1.5 J, and your VB prime will be, the X component was 1.22, so 1.22 I minus 0.707 J. Since these are vectors, you can actually find the components they make, right? You can find the magnitude and the angle. We can actually find these angles. This angle here you can find. This angle here you can also find. This is vector, so tan inverse Y component. Actually, I can even give you those numbers. I think I did calculate those. If we call this theta 2, and we call this phi 2, you can find theta 2 by saying, well, that's tan inverse 1.5 over 1.26. I just put the positive because I know where that angle is. Opposite over adjacent, that'll give you, I'm surprised that I have these numbers, 50 degrees. 50 degrees, or at least approximately. Double check these numbers. Phi 2 is tan inverse 707 divided by 1.22. Since I'm just finding the angle with respect to a negative direction, I'm just ignoring the minus there. That'll give you about 30 degrees or 30.1 degrees. All right. So now you exactly know the velocities. This is not what we were asked to find. We were just asked to find the X and Y components, to find the X and Y components. But knowing the X and Y components, you can also find the angles and the magnitude of velocities. Magnitude, and you can also find the magnitude. I won't do that. All right. So knowing the information before the impact, could find the velocities after the impact. Now, again, for the 5th time today, very, very careful. Be careful about the signs. When we derive the equation for this direct central impact, which for an oblique impact would be what we write for the impact along the line of impact, or X, we assume everything is positive. So whenever you have a negative value, make sure that you're putting the negative value. Okay? As long as you put the correct values for before the impact, whatever you find after the impact is going to be correct. Right? You don't know about after the impact, so you really cannot make that much of a prediction about that. Right? But if you have information about before the impact, we should be able to identify the components and the signs. All right. Question on this one. R cosine, find the y direction. Let me see if I understand what you're saying. R cosine of VB prime. Wait, so in this triangle, you're saying I have V, for instance, let's go with VB. We have VB prime X and VB prime Y. And then Y direction, this would be VB prime. Once we have X, well, we don't have this angle though. I mean, this angle here, we don't know what that is, right? Because we found this based on the vectors we calculated. Because we have no information about velocities after the impact. We don't know what angle they make with line of impact or plane of contact. We don't know what is their magnitudes. We have to find basically everything. All right. Question on this one, guys. Hopefully this example clarifies, this one and previous one clarifies the whole idea of leak impact and how to deal with directions and signs. All right, no question. So we have time. I have one example. It's not for oblique impact. It's actually for direct central impact, but it's a combination of direct central impact and energy methods. And I think it's good to actually go over that and just, it makes sense, but it's good just to practice and to get a sense of mixing these two together. We did that for the example with the bullet and the box, right? But let's just take one step further and do something that needs implementing energy methods twice before and after the impact. Again, that's something that you probably understand and you see. I think it's one of the problem in one of the practice problems, but now that we have time, let me just go over that example. And it's good to just remember that when we are studying an impact, we are looking at immediately before the impact and immediately after the impact. These velocities we found are velocities immediately after the impact, and the velocities we were given were velocities immediately before the impact. Right? If you pay attention to the way the problem is phrased, it says find the velocity of each disk just after the collision. If you wait longer, the velocities are going to change depending on if there is friction, if there is one of these is going upward, there is gravity, so velocities are going to change. We're just talking about immediately after, immediately before the impact. These are the velocities. Now, here, one point, write a note somewhere to remember that it says two smooth disks, so you don't have to be worried about friction. But in so many cases, they might not even say that. They might even say there is friction, and they don't give you any information about friction. Right? There is a good logic, or you can make this case saying that, well, the impact is a fraction of a second, or maybe very short period of time. And because the energy exchange and the force in this impact is too high, is a large impact, is a large force in a short period of time, even if there is friction, we can ignore that external force because we are looking at a very, very short period of time. And so friction can be neglected for like half a second if we are exchanging a lot of energy. The friction there is not really playing that much of a big role anyway. friction plays a role in a longer period of time when the object starts moving across the surface, slowly takes energy out of the system. But in a short period of time, because the forces involved in an impact are large or usually huge, you can think about the car accident. Right? In a second, in a fraction of a second, two cars hit, or a car hits a wall. The friction between the car wheel, the tires, and the ground really is not that important in that fraction of a second, considering how much energy is exchanged and how much force we are dealing with during an impact. Right? That friction is totally negligible. So just keep that in mind. So many cases we can just easily ignore the friction during an impact. Right? Just during the impact. Remember that. All right. Let's do this example quickly. We have some time. So we have this, again, it should be relatively familiar if you went over practice problems. But we have this pendulum, two pendulums. One is right there hanging. I might be able to do a better job. Nope. Apparently so bad, it does not identify that. All right. I tried. Mass M. There is another pendulum here. We release it from some angle theta. Right. Pendulum A. This is B. This angle is theta. This length is L. This mass is also M. And here is the problem statement. It says two small balls, each of 1 kilogram mass, hanging from, does hanging have 2 G's there? I don't know. Hopefully I wrote it correct. From strings of length L. So this is also L, right? We release the left ball, or ball A, from rest with some theta. So the left ball is released from rest with theta equal to 35 degrees. So pull it all the way 35 degrees and then let it go. Comes down, it starts moving downward. It at some point when theta is 0, it hits ball B, right? So there's an impact there, and then after that, well, whatever happens after the impact. So let's see what we are trying to do. So it says the coefficient of restitution of the impact is equal to 0.9, right? Some weird sentences here, but through what maximum angle does the right ball swing? All right. So release it from theta, comes down, hits ball B, then after the impact, B starts going upward and it reaches some maximum height and angle. We want to find that angle. All right, so here is the situation. We have to use energy method before the impact. We release it, gets all the way to find the velocity just before the impact. Then knowing the velocity just before the impact and knowing the coefficient of restitution, we can find the velocity of both balls just after the impact. Then again, using the principle of work and energy or energy method, knowing the velocity of B immediately after the impact, and assuming that it goes all the way up to some point that it stops, we have to find how high it goes to find that angle. So that's the general idea. Principle of work and energy, impact, principle of work and energy. Right? So I'll go over it a little quickly, but that's the general story. The velocity of the balls immediately before the impact, right? Well, we say principle of work and energy would be U from, well, we can just look at it as direct central impact and then put the velocity of B 0, right? Because even in direct central impact, one object can be stationary, right? It doesn't have to be oblique central impact. We have the equations, you just plug in the 0 velocity. Right. We'll do that. So work done from 1 to T is equal to change of kinetic energy from 1 to 2 is equal to change of kinetic energy from 1 to 2, and by 1 to 2 I'm talking about this here. This is 1 and this comes all the way here, it hits the ball, so this is 2, and ignore the diameters or radius of these spherical balls, or these balls are spherical, and assume that theta gets to 0, right? So ignore that little bit of gap there. In reality, it's there. So change in height would be mgl 1 minus cosine theta. So that would be mgl 1 minus cosine theta. Since we're going downward, is positive. And the kinetic energy is released from rest. So that becomes 1 over 2 mv2 squared minus, we're just looking at ball A. I just remember that. Impact. Velocity of balls immediately before the velocity of ball A immediately before the impact. This is better. So VA squared, I'll just go with VA squared. This velocity at the beginning, 1 over 2 mv2 squared minus 1 over 2 mv1 squared, right? V1 is 0, so the second part is gone. And the velocity at before the impact is VA. I'll call it VA. From there, you can find VA. It becomes 2. You can cancel m's from both sides. It becomes 2gl 1 minus cosine theta. If you plug in the values, you know theta is 35 degrees. G is G. Tell me L is given somewhere. I forgot to put it there. L is equal to 1 meter. Just fix that in problem. I forgot to put it. So L is 1. You can calculate this value. You'll get 1.88. I don't know why they go that far. 367 meter per second. So this would be the velocity of A just before impact. This is energy method. remember we talked about pendulum. If you don't know where they get that MGL1 minus cosine theta, just take a look at your notes from before. That's the change in height. It's delta H. I won't go into details for that. I believe we can figure it out. We are on MGL cosine theta at the top. When we get all the way at the bottom, it becomes MGL, and then we find delta H, which is MGL or MGL minus L cosine theta. I can't apparently help it. This is delta H, which is L minus L cosine theta. All right, so once we get velocity just before impact for A, well, velocity for B is 0, as Alessio mentioned, right? So for impact part, we have two equations, right? We say MA VA plus MB VB is equal to MA VA prime plus MB VB prime. And well, VB is 0, so this is 0. VA, now we know it, right? MA, we know it, it's 1 kilogram. MB is 1 kilogram. This is 1.88. Let's just put 4 here. So we get one equation between VA prime and VB prime. Velocities after the impact. This is direct central impact. When A gets here, or it hits B, right? And the coefficient of restitution, right? It was VB prime minus VA prime divided by VA minus VB. Velocity of B is 0 before the impact, right? Coefficient of restitution is given 0.9. So you get another equation between a relation between VB prime and VA prime. So from there, you can actually find you will get VA prime plus VB prime as it becomes actually 1.884, because that's just 1 and 1, and that's 1. From the second one, you'll get 0.9 times VA, which is 1.884, is equal to VB prime minus VA prime. So we get two equations, two unknowns. You will get the values, right? The velocities after the impact for both. You will get VB prime as 1.789. Rounding the numbers here. VA prime is 0.094. So although they hit each other, A still continues going to the right. The impact is not in a way that pushes A back to the left. A continues because both of them are positive, right? Velocities after the impact. So VB, ball B goes to the right, and ball A also follows ball B even after the impact. I think that happens because of the coefficient of restitution is high. Right? So now these are velocities after the impact. Right? So now we know how fast VB is going. Now we have to again write and use principle of work and energy to find how far it can go up. Right? This is the situation now. So this was step 1. Step 2. Step 3. Here is where we are. We now know what the value is, initial value is for B. Right? So it's initial velocity. So this is B. Some initial velocity is given to it, and we are told that it goes up to some point. We want to know how far it goes. So that would be B. And let's call this angle that it goes all the way up as phi. So we can find phi. So same story. T from 1 to 2 is U from 1 to 2. and the velocity, well, the initial velocity we know, final velocity we don't know. So it's going to be 1 over 2 m VB prime squared, MB VB prime squared. Here should have been MA, right? I forgot that. Final velocity minus initial velocity. So here is a negative. Remember, this is 0 because initial velocity, final velocity minus initial velocity, final velocity is 0. Maybe I should have put it here. Let me just put an explanation. 0 final velocity. And then it goes up to some height. So it's going up, should be negative minus MB. This is also MA. Some reason apparently. Minus MBGL 1 minus, oops, sorry guys. I know we're done. Just give me a minute to finish this one. Apologize. We'll wrap it up. So we know MB is 1 kilogram. We know VB prime. We found it. So it's going to be 1.789 squared. MB is 1 kilogram. We know GL is 1. Only unknown is phi. Right, so from there you can actually find phi. So cosine phi would be, if I move things around, divide that, you will get 1 minus VB prime squared over 2GL, right? It's positive cosine VB squared over 2GL, and then squares 1 minus, yes. So from there, phi becomes cosine inverse this expression, squared over 2GL. I don't know why they put that parentheses there. Becomes 33.2 degrees. So if we release it from 35 degrees, ball A, it comes, hits ball B. Because of this impact, we now we can use what we learned in impact to find the velocity after the impact, or we knew how to find velocity before the impact using energy method. Principle of work and energy, and then knowing the initial velocity for the second step, right here, this is 1 and 2. This is step 1. This is step 2. B goes all the way up. All right, folks. Yeah, I kept you here way longer.